My name is John. Thank you, Kira, for that intro. That's very nice. So as some of you may already be aware, I work for a company called Helsing. We build defense software. And we have a booth out there. You can come harass me afterwards about all the things I say that are wrong in this talk. But at Helsing, we end up building a bunch of software that requires various kinds of expertise. We need to hire people with talent. But that talent is not necessarily in Rust. Some people come in, they have a lot of talent when it comes to maybe radar systems or sonar systems, or maybe they've built a bunch of image compression stuff in C++, or maybe they are really good at some aspect of physics or about control systems. Whatever it might be, they might come to us with relatively little Rust knowledge, and they need to be brought on board quickly, safely, and to the point where they can actually take that expertise and put it into practice in real systems. And I end up obviously being pretty involved in a lot of the work to bring them up to speed. And interestingly, the biggest stumbling blocks tend to be the same almost no matter what background people come from and no matter what path they try to take Rust. And I'm going to claim that the four biggest ones are send and sync, futures, where bounds, so trait bounds, and lifetimes. And my goal is to give you some shortcuts to jump through these obstacles, or to help others do so, to learn these things more quickly and build up a sort of understanding for them quickly when they inevitably encounter them through their learning journey in Rust. When I originally pitched this talk, I thought I had 60 minutes. And then I quickly realized that actually I have 30 minutes. And of course, I've now spoken to you for about 2 minutes already, which means I have 28 minutes, so we got to go. Perhaps uncharacteristically for me, there will not be a lot of code examples or diagrams in this talk. Those of you who read Rust for Recitations might recognize the style. We will have to move somewhat quickly, so bear with me. But otherwise, feel free to find me afterwards, and I'll try to give more depth to all of these things where I can. So let's go straight into send bounds. So send bounds, the sort of basic premise for send is it is a trait that marks that a type can be given away to others. The very fundamental question you should be asking yourself with send bounds is whether it's acceptable for another thread to have a mutable reference to your type. Is the microphone going in and out, or is it fine? OK, it sounds to me like it's going in and out. Great. I'll continue then and pretend nothing happened. So it actually turns out that whether another thread is allowed to have your thing or whether it's allowed to have a mutable reference to a thing end up being the same concept. Because if you have a mutable reference to a value of a type, you can use something like the memswap method from the standard library to take ownership of the type behind the mutable reference. So whether it's a mutable reference or the type itself, send does the same property. And in a way, the most core part of send is whether another thread is allowed to either use mutable reference to your type, like call methods that require mutable self, or whether it's allowed to drop that type. Most types are send because they just hold a bunch of data, like string, for example, is send. Anything that contains strings or integer types is also send. So most things are send. But there are three primary reasons why a type might not be. The first of them is external constraints, things that are imposed on you from outside the scope of your current program, things that are exposed to you by, let's say, external libraries, maybe the operating system, or maybe hardware that you're working with. These external constraints tend to take the form of the same thread that started using the thing or constructed something needs to be the same one that uses it throughout the lifetime of that thing, and also needs to be the same one that destroys it at the end. The prime example of this from the standard library is mutex guard. So if you have a mutex, you call lock, you get a type back called a mutex guard. Mutex guard is not send. What this means is you are not allowed to take a lock on one thread and have another thread drop that mutex guard and release the lock. That is not permitted. And the origins of this requirement is that the operating system, specifically Linux, the way that they provide the mechanism for us to implement locks, those underlying locks that Rust makes use of, or at least made use of in this form for a long time, did not allow you to release a lock from a different thread as where you acquired it. And so that same restriction then ends up applying transitively to Rust, which exposes that same type. The second reason why something might not be send is because it uses thread locals. So thread locals are as the name implies, variables that are local to a given thread. You declare these in Rust with a thread local macro. And if you have a type that, let's say, when you construct it, it puts some stuff in a thread local. That might be for caching purposes, it might be for performance optimization, whatever it is. But it sticks something in a thread local. It is not OK to take that type and hand it to another thread and try to use it over there or drop it over there if those things will access the same thread local. Because on the other thread, that thread local will not be the same one. It might be uninitialized, it might have been initialized by some other constructor of that type, and so that would not be safe. And the third reason why something might not be send is because of static assumptions, things where the semantics of the type or the methods that the type provides only work if it does not cross thread boundaries. The RC type from the standard library is a good example of this. So the RC type is a reference counted type, kind of like ARC, the atomically counted reference counting type. But RC does not use atomics to keep track of how many copies there are of something. And so with RC, it's just a standard like CPU addition and subtraction, which means that if two different threads try to increment the reference count at the same time, they both do a sort of equals the current value plus 1. And if you try to run that on multiple CPUs at the same time without atomics involved, you might end up with two threads trying to increment the reference count, but ending up with a value that's only plus 1 instead of plus 2. And now the reference count is wrong, and things go bad. And so RC is faster, but it is not send for this reason. Sync is very closely related to send, so it's worth talking about in the sort of same part of the talk. Sync is about sharing your toys. So where send was about, can you give away a mutable reference to your type, sync is about whether you can give away an immutable, a shared reference to your type. And it actually does work this way in practice, that a type T is sync if a reference to the type is send. That is the connection between send and sync. And because sync allows references to a thing to coexist on multiple threads, this is one of the primary ways in Rust that you get parallelism, is that you allow multiple threads to access the same thing and thus cooperate on their work on that thing. Sync, there are fewer reasons why something might not be sync. The primary one is to uphold static assumptions, sort of like how we talked about for RC. RC is a good example here as well, where imagine that you gave another, you cloned the RC locally on your thread, so the atomic increment is fine, and you give away a reference to that RC to another thread. You might imagine that that's fine, because that other thread, all it can do is use the thing shared like immutably behind the RC. The problem is the clone method takes a shared reference to self. And so if I give away a reference to an RC to another thread, that thread can then choose to clone itself, and now you run into the same reference counting problem. Other types like cell and refcell have similar things where they can only provide correctness if they know that they're never being concurrently accessed from multiple threads. And so that's why something might not be sync. And every combination of send, not send, and sync, not sync do exist. Not all of them exist in the standard library. Some of them exist more in the library ecosystem around them. But all of the combinations are valid things you might see in practice. OK. In fact, let me give you an example. So RC, as we talked about, is not send and not sync. Mutex guard is not send, but it is sync. Cell is send, but not sync. So cell, if you have a cell, you can give it away to another thread, and that's fine. But you cannot concurrently access it from multiple threads at the same time. And for understanding why, I recommend you either go read the docs for cell or watch the video I did on this, because it takes a little while to explain. But it is pretty cool to be able to rely on the type system to give these kinds of guarantees. OK, so that's send and sync. Let's talk about futures. Futures is a topic that I think tends to confuse Rust developers endlessly, and people never feel like they really, truly get it. And so I'm going to try to explain futures to you in about 3 minutes, and we'll see how well that goes. So I think the core insight for futures is that they are nested state machines. Every x.await, where x is some future, embeds x into the current future. So it produces a larger future that embeds the state machine of the thing you await inside of it. As a result, futures can get big. If you think of writing an async fn, for example, every time you call await, the future you're awaiting gets put inside the future that that function returns. And that keeps expanding, going out, until you end up with this giant future at the top. So that could be your async fn main, for example, and just ends up as this humongous future at the top. If you walk back up all of the await calls, that's where you end up. You end up with this top-level future, and this is what is often referred to as a task. The tasks are the only thing that are visible to your asynchronous executor, something like Tokyo. What Tokyo will do, and all other executors, is that they will call poll, the poll method from the future trait, on the top-level future, on that task. And then that poll will call the poll on whichever future last yielded. And that will call the poll on whatever future last yielded, all the way deep inside that nested onion of futures, nested sequence of state machines, to get back to the place where you resume. As a result, there are a couple of things we conclude. First of all, executing a task is single-threaded. One thread calls poll at the top of the task, and that recursively calls poll all the way down to resume your future. And that means there is no place for there to be parallelism. There is no place for another thread to be executing any single future. The other thing we can observe is that if you have deeply nested futures, you might actually end up with resuming a future taking a decent amount of time, because it needs to call all the way down into the most deeply nested state machine where you last yielded. So you might go, well, OK, how do I get parallelism? And what about concurrency? And the two are different. The runtime only knows about tasks, these top-level futures. And so the way that you get parallelism with asynchronous code is that you have to be able to tell the runtime about a future that you want to sort of hoist up. You want to make it be a top-level task. And this is what the spawn function is for in most of these libraries. You give it a future, and instead of embedding it in the current future, it takes that whole future and gives it away to the runtime and says, this is a new top-level task now. And then when the executor runs a bunch of different threads, those threads all get to work on different tasks, so different top-level futures, at the same time. And that's how you get parallelism. And so you might wonder, well, what about things like the select macro or the join macro? How do those work? Those give you concurrency. They give you the illusion of parallelism, but they are not actually parallel. Instead, they are very rapidly sequential, sort of behind the scenes. So when you use something like a join or a select, what actually happens is that recursive sequence of poll calls will, when it hits something like a select, it sort of has a list of futures, and it calls poll on each one in turn. And so that way, it looks like they are all executing concurrently, but in practice, they are being polled sequentially. You need something like spawn to get actual parallelism for multiple threads. OK, so let's then look at the combination of these, because this ends up being a combinatorial problem that I need to explain of all of these four things interact with each other, which is part of the reason why it gets complicated. One thing you might have run into is, why isn't my future send? Right? This is an error I think we've all seen from the compiler of like, this future isn't send or this future isn't sync, and then we get some giant piece of context trying to explain us why. Let's first start with, why do futures even need to be send? The reason futures need to be send is because if you have a multi-threaded runtime, asynchronous runtime, then imagine that you're on one thread and you want to spawn a future, so you want to give away a top-level task to get parallelism. Well, that task, that future, is going to be run on a different thread from you. And so therefore, it must be sent because it's going to be given away. But even during the execution of a future, like imagine a future is being polled and then it ends up yielding, you could imagine that all of these worker threads that Tokyo has all have queues of the futures that they're going to continue working on when they finish the current one. Imagine that you have two workers, and one of them has a very long queue and is really busy, and the other one sits idle. You might want that idle one to be able to sort of take some things out of the other thread's queue so that you do get that parallelism. But that requires, again, moving it across thread boundaries, and calling poll requires a mutable reference. Therefore, the future must be sent. So when is a future sent? Well, there are two rules that need to be in place for a future to be sent. The first of them, and this is hopefully intuitive, is that everything it captures from the environment, all the stuff that goes into the future, must itself be sent. And this is because when you construct the future, it also constructs all the things that were inside, so you need to send those things as well to send the future. The second one, and this is what tends to trip people up, is that anything you hold across an await point must also be send. So imagine, for example, that you take a standard library lock, you get back a mutex guard, then you call await, and then you try to use that guard. There are a bunch of reasons why you probably shouldn't do this, but one of them is that the mutex guard is not send, as we talked about before. But when you call that .await, your future might yield. It might find that there's no network traffic or nothing in the channel or whatever, and so it ends up on the queue. And then work stealing might end up with that future being moved to another thread. So that means the mutex guard now also has to be moved because that's part of the context for the future. And so this is why everything that's held across an await point must also be send for the future to be send. And as we learned with sync, that means that any reference that you hold across an await point needs to be sync. Because again, reference is send only if the underlying type is sync. And so this is how you often end up with futures not being send because some type is not sync. OK, moving right along. The next thing is lifetimes. A bunch of people have tried to explain lifetimes in a bunch of different ways. The mental model I have that I have found the fewest problems with, that's not to say it's perfect, but it works decently well, is to think of lifetimes as a consume by date. It is sort of the last time where it's still OK to use a given thing. There's also a sort of sub-question, which is it OK to use it at every intervening point before that time? But let's put that question aside. That gets complicated fast. If you really want to understand more about lifetimes and borrows and the like, I highly recommend the write-up about tree borrows, which is one way to try to formalize Rust borrowing mechanism. So Niven Villani has written this excellent page going through how tree borrows work and basically giving a more structured explanation of how lifetimes work or should work. Highly recommend you go read that. But without that context, let's try to explore what lifetimes really are and how you should think about them. So lifetimes are the primary mechanism that allows Rust to avoid use after free and allows to avoid concurrency bugs. It is the thing that makes sure that you do not have two mutable references to something at the same time. It is the thing that ensures that you don't try to use something after you've dropped it. That is what lifetimes are for. And that's where this consume by date idea comes in, is that the consume by date will be set such that as long as you use it before then, you're not conflicting with another mutable reference, your thing hasn't been dropped, like it's safe to use. But after the consume by date, there are no guarantees. It could still be fine to use, but you don't have a proof that says that it's fine to use by that time. So it's one of those like consume by but often good after, except the compiler says often good after is not good enough. We only allow programs where we have a true proof that you stay within the consume by date. And so one question I very often get on lifetimes is, well, why do I never need to write multiple lifetimes? I feel like I only ever write tick A and never tick B or tick C. Why is that? Well, the answer to that is because lifetimes can usually be shortened. Right? So if you say something has to be consumed by, I don't know, January 2025, then it's OK to say that the consume by date is November 2024, because that's shorter. So in general, lifetimes can be shortened. So imagine that you have a function that takes multiple references, and each reference has a different consume by date. Right? The thing they refer to might be dropped at different times, or other references might be taken later, so they all have slightly different consume by dates. If you just specify one generic lifetime argument, one tick A, what the compiler will do is say, well, I'll just take all of the references you gave me, I'll pick the shortest lifetime, the shortest consume by date, and I'll just say that they all have that consume by date. So it only really needs to store one lifetime. This is really handy. It means that we don't end up with tick A, tick B, tick C, tick D on like a bunch of different functions. But you might wonder, when do I need tick B? When do I need multiple lifetimes? And the answer to that is, if you ever need to return something from such a function or from such a type that holds lifetimes, and the thing you return should have a longer consume by date than the shortest consume by date that was passed in. So imagine you take two string references in, and one has a short lifetime and one has a long lifetime. If you just write tick A, those will both be stored with the short lifetime. You cannot then write a method on such a struct that holds these two string references that returns a string reference with a longer lifetime, because you can no longer name the long lifetime. The tick A refers to the short one. So having multiple lifetimes is for when you need to keep separate these lifetimes. You're not willing to shorten them. When you get compiler errors that say things like, so-and-so doesn't live long enough, what the compiler is really telling you is that there's missing proof. It's not to say that it's not OK to use it here. It's that the compiler cannot be 100% sure that it is safe to use here. It cannot prove statically, based on what's written in your code, that this is OK. Now, missing proof can be a borrow checker bug. There are borrow checker bugs. I will not pretend the borrow checker is perfect. For example, Rust issue 54663 has bit me so many times I remember the number. But see Amanda's Polonius talk tomorrow for one of the ways in which the borrow checker is going to become a lot better. We're all very excited for that. But most of the time, the borrow checker is right on the money. And you need to structure your code differently to be able to articulate the proof so that the compiler can understand. Sometimes it is just impossible to statically guarantee that the lifetimes will work out, to statically guarantee that the consumed by date is right. And that is what unsafe is for. This is the main thing we want unsafe for. There may be three, but this is one of the primary ones, which is when there is there are invariants in the code that make it so that a given lifetime is OK, that it's OK to use a value at a certain point in time in a certain way. But those invariants are not written down in the source code. Like, the compiler cannot check it for you. You just know because of some other invariant property of the overall system. So that's when you use unsafe to tell the compiler, please allow this code, even though you don't think it's OK, because I promise it's OK. I've checked. You should not make that promise lightly, but that is what it's for. OK, so let's talk about where bounds. Where bounds, or trait bounds more broadly in Rust, are there to make the proof burden explicit. And let me explain more about what I mean by that. The goal of where bounds, and the reason we have them, is to make sure that everything that's used in the body of a function is implied by what's written down nearby that function or elsewhere in the program. To be a little more helpful with that, when the compiler looks at your functions, very basically, the body of the function, the code in the function, is only checked against the signature of that function. And then the signature is what is checked against all the callers of that function. These are two separate steps. Crucially, the body of your function cannot be written in such a way that it's correct only for a particular caller. It has to be correct with respect to the function signature as written. So for example, if you write the body of a function that just assumes that a particular generic type is, I don't know, debug, and you know that every time you call this function, that type is debug, then Rust will still not accept this. It is not OK for it to happen to have worked out. It must be written down in the function signature that this type must be debug. And then that is checked against callers, and that is checked against the body. There are languages that work differently. There are languages where these constraints are inferred based on how the function is used. Rust is not like that. Rust requires that they are explicit. The body of the function is not allowed to make any assumptions about generic parameters except what is written down and what is implied by what's written down. You don't get to write code just because it should have worked given the other code I've written. There are a couple of rules you should be aware of when it comes to trait bounds and where bounds. And two of the main ones that come up is that bounds on the definition of a struct or an enum or something must be repeated on every block that talks about that struct, whether it's another struct that embeds it, or whether it's an impl block or an implementation of drop. So if you have a struct foo that's generic over t, and in the definition of that struct you say that t must be clone, every impl block must say impl t foo t where t is clone. It must be repeated in every derived block. Similarly, any struct that tries to embed your struct must also require that the type they pass in is clone. This is one of the reasons why we generally recommend the trait bounds are not put on the definitions of a type. They are only put where you actually need the bounds, because otherwise you end up with this proliferation of bounds that need to be put everywhere all of the time. There is an RFC 2089, that has this notion of implied bounds, where if you have trait bounds on the generics of a struct, then you don't have to repeat them everywhere. They're implied, they're inferred. But this has not landed yet and probably won't for a while. The other thing you should be aware of when it comes to trait bounds is that any bounds you put on the drop implementation must also be on the definition of the type. And this kind of makes sense if you think about it, right? If you have a type foo generic over t, and then you implement drop for foo t, where t is, I don't know, hash, then what happens if you have a foo t where t is not hash? Does it not get dropped? Does something else happen? It gets really strange. And so there's a requirement in Rust that bounds you have on drop must also be on the struct, and therefore also must be on all the impl blocks. I've now gone through the 4 things. And so then, 4 things. So let's now look at more of the ways in which they interact with each other. Let's start out with where and lifetimes. You might have heard the scary word of higher ranked trait bounds, or HRTBs. Higher ranked trait bounds are not as complicated as they sound. Sometimes they're complicated because when you use them, they end up like requiring you write a bunch of code, but fundamentally they're not that complicated. The idea of a higher ranked trait bound is that you want to have a generic where you say that the generic implements a trait for any lifetime. So if you look at the examples here on the right, you'll see the first one, which is an example of something that takes an f, where f is a function from a reference to a U8, and it returns a reference to a U8. But crucially, the lifetimes of the input argument and output argument should be the same. You couldn't write generic over tick A here, because if you wrote generic over tick A in your function definition, then that would mean a specific lifetime. The caller passes in a lifetime, and you check the bound for that lifetime. What this is saying here with the for is saying for any lifetime tick A, f implements the following signature. Similarly, for the next line, it's saying for any lifetime tick A, t can be added to by a string reference with that lifetime. So it's not any particular lifetime, it's any lifetime. That's all higher ranked trait bounds really are. They're a way to say, for any lifetime, the following is true. We only have these kinds of for all bounds for lifetimes at the moment, and for the foreseeable future. You cannot say for any t, or for all t, f is a function from t to t. That's not a thing you can currently write, and probably won't be able to for a while, but you can do it with lifetimes. And that's also where it's most useful in Rust. The next one we can look at is the combination of where bounds and futures and send. This is where you often end up with this like syntax soup in Rust, because remember, with where bounds, you must be explicit about all of the things that you assume. So you have to write a bunch of things out. With futures, you have to make sure that they're send, that the things that they capture and return are send, and so you end up with these sort of cascading list of requirements, all of which must be explicitly enumerated. And that's how Rust ends up with this, I think, reputation for having a bunch of text. Like there's a bunch of stuff you have to write. And it's true, but if you look at this code, the bounds actually make a lot of sense as you start reading through them. Here is a function that's generic over f and some type fut, where f is a function that returns this other generic fut, representing a future here. So basically, f is an asynchronous function. Fut implements the future trait and also implements the send trait. We want it to implement both so that we can run it on something like the Tokyo executor. And this last line, which often trips people up, is that if you have fut, you treat it as an implementer of the future trait, which is fine because we said that it implements future. Then the associated type output of fut's implementation of the future trait is send. What that last bound is saying is that the thing this future returns is send. Which makes sense. If we want to run it on an asynchronous scheduler with work stealing, you need to be able to get the value out from a different thread as well. So it's verbose, but it's explicit. The last thing that I want to point out with where-bounds is they're actually pretty flexible. There's no requirement that you put t on the left. There's no requirement that you even use t at all. You can write all of these where-bounds are totally valid. Not all of them are useful, but they're valid trait bounds that you can write. So when you write where-bounds, try to avoid the instinct to put all of it on the left, because it tends to make the trait bounds really hard to write and hard to read. Think more about what you're actually trying to guarantee. Things like the second one, if what you care about is whether you can share an arc t over thread boundaries, you should write where arc t is send, as opposed to figure out what the bounds are for an arc to be send, and then write t is send plus sync. You can write this instead and be more explicit and also more concise. That last one, where string is clone, totally valid, mostly useful for testing, where you write your own types in here and say that, check that your own types are send. But it is stuff you're allowed to write. And with that, I think I'm at time, and that's all I wanted to say. There's a bunch of nuance to all of this here. I'll be outside for questions and stuff afterwards. I'll be in the Helsing booth. So if any of this does not necessarily make sense, you want to hear more about it, you have questions, just come find me, and I'll do my best to explain more. Thank you.